Okay, great. So, hello everyone. Let's start our lecture. And actually today we will finish the so-called classical machine learning. So we will discuss ensembles and gradient boosting and random forest model. And then, so next week, we will switch to neural network models or so-called deep learning. But firstly, let me remind you our previous lecture. So we discussed the logical rules and logical models, the family selection problem, the local modifications, and the most important informativeness criteria for selecting features and thresholds and so on. Then we dive into decision tree classifier model and also discuss the decision tree for regression task. Of course, we looked at the measure of uncertainty for any probability distribution, and optionally, if you wanted, you may look at the handling missing values problem. And now we are continuing. So the notations are the same. As usual, we have x as our objects and y as our answers for any supervised task. And based on this training set, we want to train the algorithm which will give us the ground truth, the most closest to ground truth labels. And here we consider some modifications. So you see C here, this is composition rule of raw estimates. So imagine that we have some base classifier, base algorithm, base model, which gives us the raw scores. So the R is space of raw scores. And then composition rule gives us the predictions, so the Y answers. And here we introduce new R space of all possible estimates. And yeah, so why we need to introduce some new space? Yeah, so it also can be called correcting operation. So if you have several base algorithms and each of them gives you some answer, some raw score, then based on these t different answers, you are selecting, you are constructing the final answer R again. And of course, sometimes we can predict answer based on the real answers, Y answers of our base models, yeah. But in general, and also in classification tasks, the set of all the mappings from raw scores is significantly wider. So we may use them to enlarge our possibilities and to have much more degrees of freedom and to eventually to predict better than only with answers. So okay, consider some examples of correction rules and estimation spaces. So if we have binary classification problem with two answers, -1 and +1, and our maybe simple algorithm can be sine of the raw score from base model. Yeah, so sine of b from x. And here you see the raw scores come from R, some real number. Then the final rule gives us the answer from the binary set. It is either -1 or +1, depending on the sign of the base algorithm answer. Then, so in second example, we have multi-class classification problem with more than two classes, yeah? So 1, 2, 3, and so on till m. And here, again, we can choose the final answer based on the raw scores of each base model. You see here, we need to maximize the score from based algorithms and choose the predicted label as the maximum from all raw scores. Yeah, and here you see again the base model gives us m scores, and then we choose maximum score for the current label of this object. Yeah, and this is our model. So our algorithm simply chooses the maximum score of all the basis algorithms and gives us the final answer. That's the examples of rules, different rules. And if we have regression task, then there is no need for composition rule. We can simply take the raw score from the base algorithm, and this is our answer for the original task, because this is regression problem with real value as answer. Okay, so let's go on to the examples of different ensembles or correcting operations. So imagine again you have several base models, for example T, and maybe the most simple ensemble is simple voting. So your answer is the mean or average answer from all the base classifiers. Yeah, and that's it. You simply sum everything and then divide it over the number of your models, of your base models. Then you can think about more complex approach. So this is weighted voting. Then you want to adjust weights based on the different models. So suppose you do know something about the underlying structure of your base models, and that's why you want to weight them. Yeah, and then weighted sum gives you the new answer. It is possible sometimes the sum of all the coefficients alpha is 1, sometimes it is not 1. Both variants are possible, and yeah, it works too. And maybe the most complicated rule, yeah, the so-called mixture of experts. There you see, instead of simple weight, which is one and the same for all the objects, you have some solution function G. So this is your expert functions. You want to select group of objects for which you use some particular base model, yeah, and then for other group you prefer to use other base model. So here you see the GT function depends on X, on the object. So depending on the object, you may prefer different base models to get the final answer. Of course, you need somehow to train both base models and your not decision rule, but this function GT depending on X, yeah, on the object X. Okay, and there are of course some stochastic methods for building composition, so how to train several different models based on one and the same data set. Yeah, let's switch to the whiteboard and discuss how to do it. So yeah, you see here, so we actually have two general ways. So the first way is called bagging, or it is the same as bootstrap aggregation. So B from bootstrap and egg from aggregation. So bagging, it simply means that you subsample from your data set new data of the same length L with repetitions. So each time you have new data set for training your model, and the ratio of object falling into the sample is approximately 0.6 or 1 minus 1 over exponent. or vice versa, you can choose, you can select the random or some certain subsets of features. So if you remember the general statement of a machine learning problem, then you always have so-called object feature matrix. Yeah, so this is the x1, x2, and so on, xl objects. Yeah, and columns of these metrics are all the features. So this is feature 1 for object 1, then feature 2 for object 1, and so on, feature n for object 1. And here goes feature 1 for object 2, and so on. Yes, so feature 1 for object L, and so on. So this is your object feature matrix, and you can select the either some rows of this feature, and this is begging, yeah. So some certain objects, not all of them, yeah, no, not the whole data set, or you can select the rows, yeah, the columns, sorry, the columns of your matrix, and it is called RSM, or random subspace method. And based on these two ways, you generate different data sets. So the data set 1, data set 2, data set 3, and so on. When you train maybe one and the same, maybe different models on these different data sets, and it gives you a lot of base models, base algorithms to build composition on this fundament. Okay. Yeah, let's go on. So this is the picture of the result for some data set, and so left picture is simply averaging of different decision tree models without any bagging or RSM. And the right picture is bagging on the same data set and the same model of decision tree. So you see here the final result is almost the same, so a simple averaging and bagging for decision tree model. But the variance of our answers here are much fewer, so for bagging. And of course it's good for us. We can approximate, we can evaluate the answers based on so more effectively than for the simple averaging. Okay, and now let's switch to the boosting method. It is really workhorse for table machine learning tasks, and actually the idea is really simple. So imagine that you have some target function of your problem. Yeah, you want to approximate a function f of x, and so at the current step you have some model that predicts the answers for example based on the decision tree model. Yeah, and of course you can calculate the difference between target function and the current prediction. And this difference is plotted here on the right side. So then you may, so given the residual, this is the difference between f and d, you are trying to build next decision tree model to predict the difference between and to decrease the difference of the current target function evaluation and the ground truth target function. Yeah, so this is the idea of the boosting method. Each step, each new decision tree simply tries to reduce the overall difference between target and current answers. Yeah, so there are some formulas. Let's consider some example problem. Let's say it will be binary classification with reject, so we can have 0 as a result as reject from classification. And our based model will be simple voting. So here you see we have t-based models, then we average their answers with weights alpha t, and the sign of this combination, of this sum, is the current answer, okay, a from x. Then, of course, we can count the number of errors for the whole dataset XL. So the current number of errors is, what is it? Is the ground truth answer, y, multiplied by the prediction, so this is the current answer. And if the sign of the multiplication is less than 0, then it means that we have error on the xi object. Yeah, so we count all the errors, and this is our empirical risk. This is our average loss function for the data set and classification task. Yeah, and based on this, we can we are trying to decrease the number of errors. Yeah, so of course we need to approximate this function so to get smoother loss, but let's do it next slide. And here we can consider two main rules in boosting model. So then you fix the first t-1 base models with weights. You need to adjust, you need to tune, to train a new model. Yeah, so the BT model with alpha t weight. And then you simply add these answers result to the previous sum. And the second heuristic, you need somehow to approximate the number of errors. So you want to use the smooth approximation of direct loss function. Yeah, so we want to reduce the number of errors in classification, but we want to calculate gradients. We want to understand what is loss, to get it to have loss as close to 0 as possible. Yeah, that's why we need to approximate our loss function. And if you remember, one of the possible ways of approximation is exponential function. So let me again plot the new smooth approximation of loss function on the whiteboard to remember what is going on. Yeah, to remind you. So for classical, for number of errors, yeah, function, we have something like that. This is our margin. So this is the multiplication of true answers, yeah, and the answer of algorithm. And for binary classification with -1 + 1, the a from xi. Yeah. So if the margin is positive, then we have no error. If margin is negative, then we have error, and we need to add 1 to our. So the loss function is 1 on xi object. Yeah. So the plot is looks like this. Yeah. So here is some vertical line. Okay, and of course we want to approximate this blue line with some other function. And one of the way to do it is considering exponent to the power of -m. Yeah. So then here the exponent to the power of 0 will be 1. And then if the margin m is big enough, so is positive and big enough, then the loss goes to 0. Yeah. And vice versa, if the margin is negative and big enough, then the plot goes up. So we have really huge penalty for errors for our model. And this is the possible approximation of the number of errors in our loss function. And of course, we can optimize this q tilde function with any algorithm. And this is it. So for each object, we simply calculate the exponent to the power of minus margin for this object. And the minus margin is the product of y and previous sum, the previous answer. And then when we add next algorithm here, we simply have the multiplication of two exponents, and you see for new algorithm, so for training new model BT, the previous answer and exponent from it is simply weight, simply weight in our loss function approximation. So the algorithm we will consider next slide will call so it is called ADA boost, adaptive boosting, and that's why it is adapting. So we introduce new normalized weights for each object, and we can count two numbers. So the number of errors or negative answers for the model composition, so this is n, and the number of correct positive classification for weights u, this is p, positive. And so given these two numbers, we can evaluate the quality of our current model B, and changing the model B, we change these numbers. Of course, we want correct number P goes to maximum, and negative or erroneous number N goes to 0. We want to decrease the amount of errors. So, and that's why we actually have classical variant of ADA boost. So based on these two numbers, P and N, we can prove that for any base algorithm B, which classifies the data set at least slightly better than at random, so the amount of errors, weighted amount of errors is less than 1/2, the minimum of our approximation for amount of errors is reached when the BT equals argmin of negatives, and the weight alpha t equals to the 1/2 of logarithm. So this is simply a mathematically proven fact. And using these formulas, we can build the algorithm which is called ADA boost, adaptive boosting algorithm. So the input of algorithm is all the training sample and the parameter t, which is number of base models. Then, firstly, we fix some, so we initialize some object weights. For example, uniform weights for each object. This is Wi, and 1 divided over L. L is the size of data set. Then we perform iterations. So each t is the new base algorithm, and we train the new basic algorithm using formulas from previous slide. So BT is argmin, so we minimize the negative weight negative characteristics of our algorithm B, and we of course we maximize the positive answers for our current algorithm B. Then we update weights with the exponential formula because we understand what is going on. We actually approximate the number of errors with exponent margin, and that's why we update weights for each object, and then we repeat the procedure for t equals 2, then for t equals 3, and we build the composition, the sum of base algorithm with weights alpha 1, alpha 2, and so on till t. So And then in the end we have we have working composition, and it is called ADA boost algorithm. It works pretty well for especially comparing with simple models as decision tree classifier or logistic regression. Okay, now let's have a break for let's say for 5 minutes, and then we will continue with gradient boosting algorithm, gradient boosting model. If you have any questions, please ask or write them in.
I have a question.
Yeah, sure.
So on one of the first slides there, you talked about how we should split up the data based on rows. I think that was called bagging. So I have a question. If we tackle
Yeah. Actually, if you want to build to build composition on strong models as LightGBM or XGBoost, they are already pretty strong because of boosting algorithms. So inside the algorithms of building the LightGBM model, for example, inside this procedure, you've already have bagging inside. So each part of your composition will be trained on different part of data set. Okay, so it is already include bagging inside boosting. That's why usually you don't need to do some other bagging with your hands. So you don't need to split your dataset. You simply put all the dataset into XGBoost, let's say, and then it gives you strong predictions. But if you want to use, so it is some more advanced technique called stacking. So if you want to use the answers of strong models as LightGBM, CutBoost, and XGB simultaneously, you can train your composition on the part of dataset and then check the stacking model on the hold out part of the dataset. So what does it mean? What stacking what stacking means? It means that you use only raw scores from your strong models, and you build new object feature metrics. So you use only predictions, for example, the probability of classes, and based on these predictions, you are trying to predict new, so better answers for the same data set and the same model, and this is the two one level stacking. You on the first level you have some strong models, and on the second level you have some separate model, usually very simple, for example linear regression. And your linear regression simply weights the predictions of each strong model to get better results on your test set. And it works, of course. So sometimes you need to stack deeply, so more than one layer model, and you need to split your dataset only for stacking, not for boosting. Okay. Yeah, great. Okay, great. So let's continue. Let's continue and discuss some heuristic and recommendation for adaptive boosting. So and they also apply for the decision for gradient boosting too. So usually you need to use weak classifiers, weak models as base classifiers. So the most commonly used is decision trees. Then you can even restrict your decision trees, for example, to use one and the same feature on each level of the tree, or you may consider only very simple rules for threshold rules for building decision tree and using them in boosting procedure. That's totally okay. And for strong classifiers, boosting is usually not so effective, but it has some effect too. So it has some better results as comparing to the simple models and so from even strong model. Sometimes here you need to check your error on validation set, so on holdout data, and to add some stop criterion. But generally, again, by default, boosting works pretty well even without any validation. So it overfits, but not so strong as other averaging models, or simply enlarging your one model. Yeah. So if you want to predict and if you don't want to think about overfitting, then some boosting model is your choice. And yeah, why does boosting work? Actually, because it tries to decrease your loss function. So the the direction of your training is decreasing loss function. And what are the drawbacks of adaptive boosting? So the first classical version of boosting. That's it. So yeah, due to exponent, it is oversensitive to outliers. It sometimes creates black boxes. Also, no, not sometimes. Boosting is always some black box. So you cannot interpret the results except maybe first 2 or 3 models in your combination. So you can look at the first and second maybe 3 and to understand what is going on. So what features are the most important, but then that's it. So in general, the boosting on, I don't know, 1,000 trees usually simply black box, which gives you good predictions. So very good predictions actually. And yeah, other boost requires fairly large training data sets. So the ways to eliminate the drawbacks of other boosts are pretty straightforward. So we can change the approximation to other function, not exponent to a power of minus margin. We can change the base algorithms to continuous real ones. And yeah, we can use some explicit optimization of margins. And so the difficult way of changing is implementing your own less greedy strategies for growing the composition. So here you see in boosting, we always want to predict best way to decrease our loss, and this is our only goal. That's why we perform greedy search, greedy algorithm. Now let's discuss the gradient boosting for arbitrary loss function. So it is very similar to adaptive boosting, but it applies to any continuous loss function. Yeah. Again, the beginning is the same. The answer of our algorithm is weighted sum of answers for the base algorithms. Yeah. Then we have some quality functional, some empirical risk, which is the sum of all the losses for objects, yeah, from for I from 1 to L. And the first, so here you see the previous answer, the sum of weighted based algorithms till the t minus 1. Yeah, this is our current answer. And then we are trying to build the new answer. So we add alpha multiplied by the new base algorithm answer. And this is our new loss. So comparing this new answer with ground truth, we calculate loss, and then we sum losses through all the objects, through all the data set. And of course, we want the overall loss to be as close to 0 as possible. Okay, so we want to minimize this risk on weight alpha and base model B. And how to do it? So this is looking at the formula, we understand that actually we want to minimize our risk. So we want to go to decrease the loss function, yeah. And from the previous material, we may remember that how to decrease some loss function. Yeah, we need to go along the anti-gradient vector. Yeah, so if we subtract learning rate alpha times gradient, the value of gradient, so this is the partial derivative of loss function from the current value, then we will decrease the loss. Yeah, and this is our goal. So actually, our gradient step is very similar to one boosting iteration. So in boosting iteration, we add a new answer of the base algorithm, and here we subtract the anti-gradient. Yeah. So actually, we can look for such a basic algorithm that will approximate the anti-gradient vector. And this is our mathematical statement. So the problem is how to find base model B to be as close to anti-gradient as possible. Yeah. So here is actually the difference between two vectors. The first vector is b from x, and the second vector is minus gradient. Okay. So the difference gives us plus here, and the overall expression is sum of square root of all the differences. Yeah. So this is in essence least square methods to get B as close to anti-gradient as possible. And this is our gradient boosting model. So we want to train B to give answers from anti-gradient of our current loss function in current answer. Okay. And of course we can solve this problem again as in adaptive boosting. We firstly have training set and the t parameter as input. Then we trying to build one by one the composition of base models, and for each t from 1 to t big, we are trying to approximate current value of anti-gradient. Yeah, and this is it. So this is gradient boosting. We can actually slightly change the parameters of base algorithm to approximate the anti-gradient goal. And then, so step by step, we are approaching to the minimum of loss function that is our goal. Yeah, and even here, so how to tune the weight of BT base model in composition. Yeah, so here is the second optimization problem, but it is much easier than the first one. So the first one is optimization and minimization of vectors, and this is one-dimensional problem. So we simply want to adjust the weight alpha for the fixed base algorithm. Yeah, and again, it is simply the minimization of loss function through all the data set. And then we update our answers of the composition and go to the next iteration. Yes, to the next t until we get the whole composition. And this is boosting. So for any loss function which can be which is differentiable, yeah, and for any base model actually which you can tune to solve this optimization problem. That's it. So 2 parts of gradient boosting. And of course there is a more effective version which is called SGD or stochastic gradient boosting, and the only difference is that we here we use not the entire data set, yeah, but a random subsample without a placement. So this is bagging inside boosting. And the advantages of stochastic gradient boosting is improved quality and enhanced convergence and reduced training time. Okay, so this is the default, the strongest model on so-called table data. So then you have object feature metrics with different features. You actually should use some variant of gradient boosting. Yeah, so why is boosting so ideal? Really good model which performs the which gives you really small losses for different problems. Okay, so the regression task. So we discussed classification problem, and of course for regression almost the same formulas are worked. So here we should train our new model BT on differences as previously. Yes, so this is ground truth answer and the previous answer of your composition of boosting. And then if for example regression is linear, then you even you don't need to train the weight, but overall all the formulas are the same except the loss function. Yeah, so you change loss function to the square of difference, and this is solution for regression task. And for classification, if you consider the exponent function, then your gradient boosting model will exactly match the adaptive boosting algorithm, the classical variant, because adaptive boosting uses the exponent of minus margin loss. Yeah, so they will coincide. Okay, let's go on. So to the XGBoost, maybe the most popular, so one of the most popular implementation of gradient boosting over decision trees. And actually now the description of this model is really simple. It is the so you have regression classification trees as we've seen before previous lecture, and then you perform these. So you need to fix base model, and here you see the base model is simply weighted averaging of very simple algorithms, so the decision rules actually. So RG is the area of space for each leaf of your decision tree. Yeah, then you have leaf weights, and the J is the number of leaves in the tree. That's it. So this is your base model. You need to adjust weights and the areas. Yeah. So you simply divide all the space into subspaces, linear subspaces, performing building the decision tree. So as in decision tree, building decision tree process, and then with this base algorithm, you need to specify your loss function. Okay, so what you need to optimize, and here you see the loss of current answer. So you need to optimize the loss, changing base model, so training base model B, and changing the weight of leaves. Yeah, so you minimize these. This is the main goal of your algorithm. So the minimization of loss function, and then other three terms are regularization terms. So let's look at it. The most familiar to us is square, sum of square of all the weights. So here we want to minimize weights. We want them to be as close to zero as possible. Here, this is the same weight minimization, but in L1 norm. So this is the sum of absolute values. And the third term here, the third regularization term, is simply a characteristic function of non-zero weights. So we want to have as few weights as possible. Yeah. So we want to restrict our decision trees, our each decision tree based model. And here is the term to zero different weights. So it simply means to have fewer leaves in the tree. And the task even has an analytic solution for weights. So you can simply perform your iterations very fast. So as we've seen in adaptive boost, yeah, we have formula how to build next algorithm, and here is the same. We simply iterate through the gradient boosting steps with analytical formula. Okay, and other implementation of gradient boosting, yeah, there is Light GBM from Microsoft, also very good model, and cat boost. You see the cat in naming, it means categorical features. So categorical features, usually for XGBoost or Light GBM, you should use only numerical features, yeah, object feature metrics. But here in cat boost, from out of the box, yeah, from scratch, it can build classifier based on your categorical features. So it converts your categorical features into numerical one with some really nice default algorithm inside categorical boost. This is the feature of cat boost. Okay, and some comparison, yeah, with so what how to choose, yeah, what do you want to use. By default, option is using stochastic gradient boosting, SGB, and usually boosting is better for different data sets and classification classes and so on. And yeah, bagging and RSM better for small training data sets. And if you don't want to have really a huge model, yeah, so huge, not interpretable model, that's why you sometimes want to use, for example, random subsample method with decision tree. And actually, bagging and RSM can be effectively parallelized, and boosting is always performed strictly sequentially, because we need to know the previous answer to build new model based on it. So we can parallelize only the construction of new algorithms, so inside boosting step. Okay. Yeah. So, and the last model for today, based on decision tree, we can build random forest. So yeah, forest consists of trees, and again, it's very simple to understand now. So what is random forest? It is bagging, bootstrap aggregation, over decision trees without any pruning. So you use the same trees as default versions. And yeah, the feature in each tree node is chosen from a random subset. This is sampling, bagging inside. So not bagging, RSM inside. Yeah, so here you see random subset of k out of n features. So it is both bagging and RSM inside one model, which is called random forest. And the advantages of random forest, it is simple. So everybody knows what is it, and you can fast and effectively build random forest model. So yeah, this is the summary of Ensembles. It allows you to solve different complex tasks with table data. Yeah, so the important discovery that boosting generalizing ability almost doesn't worsen with the increasing of complexity T. The gradient boosting is the most general for boosting, so you can use arbitrary loss function, you can use arbitrary space of estimates R, and it is suitable for regression, classification, and even ranking tasks, so you can predict rank of the object the same way, so using SGB. So this is your by default option. And actually, so after this lecture today, you are going to have new homework assignment. It will be on Kaggle platform, and it is the binary classification task for table data. So you can try using XGBoost, LightGBM, or CutBoost. So for your solution to get better results, and you can check if it works and how it works, and tune different parameters. So yeah, maybe let me show the description. Show the description of the task. So yeah, this is gradient boosting and binary classification on Kaggle. Great. Yeah, and this is the link, the invitation link to competition. So if you open this page, you see the you have 6 days to upload your results. Yeah, and inside this description you have even baseline notebook. So with all the necessary baseline code, so to upload data, to train your model. But of course the baseline model is really simple. It's simply constant zeros, yeah, zero model. And here you can change zero model to any classification model, decision tree, support vector machine, logistic regression, of course, boostings, and check results. So your model, you will fit your model and you predict results and upload results to Kaggle here. Yeah, so this is leaderboard and some benchmarks. They are not very strong, but yeah, some decision tree classifier benchmark, and a little bit stronger again decision tree classifier, so tuned decision tree model. And of course your gradient boostings should be much higher than current score. So you will check at home. Okay, great. So let's stop here. Any questions?
I'd have a question. When stacking models, if we use a linear combination of their predictions, should the weights add up to 1, or isn't that necessarily a rule?
So the variant by default, the answer is yes. So by default, you want weights sum up to 1. But actually, it may, in my practice, there was some examples of tasks there I had different weights, even negative. Sometimes it works mysteriously, but it is actually quite rare cases. So it means if you have negative weights, or they don't sum up to 1, it means that something strange, yeah, because usually you want equally, so the distribution of information, yeah, from your data set and from answers of your models should be fully completed, yeah. If you if your weights don't sum up to 1. It is really strange. It is sometimes it works and gives you better results, but this is the sign to dive into the problem and to understand why it is going. Maybe you have some error inside your implementation, some bugs inside. It is also the case.
Okay, thank you so much.
And yeah, you can try stacking in these home assignment and look at the results. It definitely should work. So I suppose the stacking of different boostings will give you the best possible score. Yeah. Okay. Any other questions? Okay, great. Then see you next week. Yeah, and we will start the deep learning stuff.